All right, um, there are a couple of functional groups that I wanted to um, clarify. So this functional group was the oxime, and it is produced by a reagent called hydroxylamine. And I think if I had worked with you guys to spell that out yesterday, we would have understood that hydroxylamine is a great name for a reagent that has both an alcohol and amine, but no carbons. So hydroxylamine is NH2OH instead of NH3. I'm not sure, why they chose amine to be the primary functional group there. They could have also made it amino alcohol. Maybe that just doesn't sound as cool. There's this other functional group that we're not going to see very much, but I want you to see a derivation of the imines. This is called a hydrazone. What is the similarity? What is the difference between oxime and hydrazone? Correct. There's that carbon-nitrogen double bond, plus then the nitrogen is bonded to something else. And then just review for me what this functional group was called. This was the imine, which can also be called a Schiff base. I think you can understand why it's a base. The nitrogen has a lone pair. That lone pair can donate, whether it be to a hydrogen or whether it be to a metal ion or whether it be to an electrophile of some other kind. This is referred to as a Schiff base. The Schiff base is just a name for an imine. So if oximes form from from hydroxylamine, plus we're going to learn they form from carbonyls. It's this combination of hydroxylamine with a carbonyl. Actually, all of these, because we're in our carbonyl section, form from a reaction of some reagent with this carbonyl.
Have the enamine being N2Rs?
Yes.
N to N? 2Rs? Is that right?
So the enamine is when you've got a carbon-carbon double bond. No nitrogen double bonded. Only one nitrogen, no double bonds to the nitrogen. We're going to talk about why that reaction forms an alkene rather than an imine. And it has something to do with the number of available hydrogens coming from the nitrogen. Okay, so I want us to look at comparisons here. Oximes form when hydroxylamine reacts with an alkene. Notice that the nitrogen loses 2 hydrogens. The carbonyl loses an oxygen. That's a byproduct of water, H2O. And then the NOH group stays. So hydrazone, the N in our 2 group stays, which means that this must form from NH2 and R2 reacting with a carbonyl. There's a very specific NH2 and R2 that we've already looked at. Do you remember the name of this reagent? We used it in the Wolff-Kishner reduction. It does the same thing as the zinc mercury hydrochloric acid in the Clemmensen reduction. Mm-hmm. Otherwise called N2H4. Do you remember it?
Yes.
It's very similar to this.
That one in the front.
No. Actually, think about how hydrazone forms when it reacts with a carbonyl, for instance, like a ketone. So it's actually the suffix we're going to change. So if you take hydrazine, NH2, NH2, H2NNH2, whatever, N2H4, and you react it with a carbonyl, you'll make the simplest hydrazone. But if you start to substitute any of these hydrogens for R groups, then you just get a more complicated hydrazone. So let's play that one more time. What would an imine form from when reacting with the carbonyl?
NH2R.
Exactly. What's another way to say that? It's an amine, correct? With what degree of substitution? For instance, we have primary, secondary, tertiary amines. Sorry? Primary. Just one substituted. So a primary amine can react with a carbonyl to form an imine. And this is what we're going to look at later. This amine already has two R groups. That makes it a secondary amine. And in all of these reactions, water is being lost. If the nitrogen doesn't have two hydrogens to produce the water, where will the second hydrogen come from? It'll have to come from one of the carbons. And that is why we get an alkene amine and ene amine. But I am getting ahead of myself. I want us to spend a bit of time looking at how to synthesize aldehydes and ketones before we start to get into the reactions with aldehydes and ketones. So I wanted to clear up some of that information based on that mistake that I made yesterday at the end of class when I was laying out the functional groups. And I also want to say this. We're going to see a lot of enamine and imine. You will come across a couple of oximes. I don't know. Yeah, actually, I think you will come across one of the hydrazones if you do one of the PLO assignments. But in class and on the tests and on the exams, you're probably going to see more focus on enamine and imine. Here's what I want you to recognize. The chemistry is all the same. Nothing changes. So if you can apply something to enamines and imines, you can apply it to oximes, you can apply it to hydrazones. It's all the same. Just different. All right. So we're going to take a step to look at synthesis of aldehydes and ketones. So you guys know what I like to do when we start to look through reactions. I want to start by looking at all of the ways we've previously seen to form aldehydes and ketones. We could do this one of two ways. I could have you guys review your notes again, or we could just pound through it, having me put it on the board. What do you guys think? The time spent in your notes is super valuable, but it means less time for me to talk. Also valuable. Yeah. All right. So let's start as far back as we can go, which is alkene addition reactions. More specifically, or maybe a better way to say it, is alkene cleavage reactions. We saw that in the ozonolysis, we can form aldehydes and ketones. So if I take an alkene like this is a good example alkene for me, because on this alkene, there is a carbon that has 2 R groups and a carbon that has only 1 R group. So I can clarify how an alkene can form one or both, one or the other, and one and or the other. Anyways. I'm just going to map my carbons here so that we can kind of see what we're looking at. So carbon 2 gets cleaved, becomes a ketone. Carbon 3 gets cleaved, becomes an aldehyde. Let's think about all the possibilities that you could form. You could form formaldehyde if you had a compound that had a terminal alkene, CH2. You could form formaldehyde. You could form formaldehyde and 1 aldehyde, formaldehyde and a ketone. You could form 2 aldehydes. You could form an aldehyde and a ketone. You could form 2 ketones. All sorts of combinations. You guys feel okay with that? Oxidative ozonolysis only forms one of these 2 groups. It can only potentially form one of these 2 groups. Do you guys know what it is? Oxidative ozonolysis, the reason it's called oxidative is because the products are more oxidized than the reductive ozonolysis, where the products are more reduced. So if we look at the same reagent and we take O3 with H2O2, our oxidizing agent, I can still form a ketone, but I also form a carboxylic acid. So for right now, that's not our goal. It's a good thing to review. Maybe I shouldn't put an X through it. Does it look like that means it doesn't form? For right now, what I want to highlight is that we can form ketones through oxidative ozonolysis, but we cannot form aldehydes. Okay. There was one other OChem 1 reaction we learned that formed aldehydes and ketones. That was alkyne hydration reactions. 2 types of alkyne hydrations. Markovnikov, or as I would like to say, oxy-Merck hydration. I'm going to take a specific example of an alkyne here. Do you guys know how I can describe that alkyne? Terminal alkyne. I'm using this to highlight the Markovnikov hydration. The oxygen of hydration is going to go to the more substituted carbon rather than the less. So this is a 4-carbon chain. And sorry, I don't have my reagents up there. We're going to add mercury sulfate, HgSO4, with water and sulfuric acid. Oxymercuration. I want to clarify something for right now. This isn't going to be a big part of our Unit 4, but it will be a big part of our Unit 5. This reaction produces an enol. I think here you can more clearly see hydration. 1H to 2H, nothing to OH. So I have added H and OH across the pi bond, hydration. This is the product that forms. It then tautomerizes, which means it goes through a chemically active structural rearrangement. That's where the hydrogen from the alcohol moves to the adjacent carbon, and the pi bond moves to form a carbonyl. tautomerization. We're going to talk more about tautomerization in Unit 5. Then we've got our anti-Markovnikov hydration, but this is better called hydroboration oxidation. Let's take this same 1-butyne. This time we're going to do a 2-step synthesis. We're going to react the alkyne with borane and follow it up with a basic aqueous solution of hydrogen peroxide, H2O2, H2O, NaOH. I want to draw your attention to something here about the borane, which is when dealing with alkynes, borane itself can cause some issues. So alternatives are often used, and the alternatives are not always clearly borane alternatives. If I get time to later in class, I'm going to pull up the active assignment that has something like this so we can review that together.
What's the last one? Is it N2.3?
NaOH.
NaOH.
Sodium hydroxide. So in this example, Markovnikov gave a ketone. Anti-Markovnikov will give an aldehyde. And don't be fooled, this also goes through an enol intermediate. The only difference here is that the enol intermediate, before it tautomerizes to the aldehyde, has the alcohol on the less substituted carbon. Okay, any other reactions that you guys can remember from OChem 1? Yes.
So you said tautomerization, that means that it can go from one to the other.
Yep.
Anything specifically about that? It just happens.
So it is acid catalyzed here, and it's base catalyzed here, which means that this tautomerization, so remember, tautomers are structural isomers, specifically structural isomers that can be chemically interconverted. I think you'll agree most structural isomers cannot be catalytically converted between each other.
But you still need some kind of catalyst or something.
And the catalyst actually comes from the reaction happening in sulfuric acid or the workup happening with sodium hydroxide.
Can you go a little bit back using the same reagent, or do you need something else?
Can you take an aldehyde back to an enol or a ketone back to an enol?
But
Yes.
According to the tautomerization, yeah, but do you use the same reagent? You have to use something else, or
What I'm trying to say is that you can't isolate this.
okay.
When you mix this alkyne with these reagents, this is what forms. But before you can isolate it, it tautomerizes because of the reagents it's in the presence of. This forms, but before you can isolate it, the reagents it's in the presence of help it tautomerize. There is actually an equilibrium between a ketone or aldehyde and its enol. I should say there's an equilibrium between all carbonyls and their enols, but the equilibrium lies heavily towards the ketone rather than the aldehyde. Or the carbonyl rather than the, lies heavily towards the carbonyl rather than the enol. Equilibrium favors the carbonyl. So you'll never find it. I remembered one other reaction that we learned from OChem 1, or if we haven't, this is a good time to review it. I'm going to call this alkyne cleavage as well. It's going to remind us of our alkene cleavage. Oh no, sorry. Bummer. Cancel it. Can you erase it? Is it too late? Don't do it. This forms a carboxylic acid. Not an aldehyde. Not a ketone.
That would be H2O2.
With ozone? Yep. Or potassium permanganate. I'm sorry, I'm realizing I think my colors here are not making a lot of sense. I want to make it clear that what I was highlighting here is that alternatives are used to BH3, but I realized that with my green, it was kind of making it seem like somehow BH3 had something to do with the intermediate. All right. In addition to oxidative ozonolysis, you can also use hot potassium permanganate. That will do oxidative cleavage as well. Okay, so that was all of our synthesis methods from OCHEM 1. What did we learn before the midterm? New ways to synthesize aldehydes and ketones.
You can go from the diol and use peroiodic acid.
Good. So diol cleavage. You know what? I think I'm gonna call this one large section of reactions with alcohols. Does that sound okay? And the first subheader underneath that will have diol cleavage. So once again, I'm going to give just a template molecule, just an example one that helps us understand what the possibilities are for our products. Can you describe the substitution of this functional group? It's not quite. Tertiary. Tri-substituted would be for an alkene, but this is a tertiary alcohol, and this is a secondary alcohol, and this is a vicinal diol. And when I interact this with periodic acid, I should get both a ketone and an aldehyde.
Is it HiCl?
HiO4, periodic acid, aka. Thank you. Yeah, I can see what that looks like, HiCl4. Periodic. All right. What else? Big class. Big class of reactions.
The oxidation.
Good. Oxidation of alcohols.
I had to make sure I said oxidation, not reduction.
So I'm going to give us a number of examples here, all right? So first of all, we can take something as simple as methanol, and we can oxidize it with PCC to form our smallest aldehyde. I want you guys to think about the nomenclature that we spent a little bit too much time reviewing yesterday, and give an IUPAC name for CH2O. Formaldehyde is the common name. Formaldehyde tells me one carbon aldehyde carbonyl attached to an aldehyde. But what would be the systematic name?
own, is that the, it would be methane,
It won't end with own because that would indicate a ketone functional group.
Of that?
aldehydes.
What is an aldehyde suffix? Al.
So it'd be methanal.
Methanal. Yep. So systematic name, methanal. Common name, formaldehyde. Okay. We can also look at primary alcohols. Here I have 1 propanol, and I'm going to react that with PCC. And this forms propanal. Why am I not highlighting any reactions with chromic acid yet? They'll form carboxylic acid, so it's not in the right review section. Good. What's up next? Secondary alcohols. We went from methyl alcohol, primary alcohol. Now let's look at secondary alcohols. What I've got here is 3-pentanal, and I'm going to put this time PCC or chromic acid. Because now I can't form a carboxylic acid. Secondary alcohol, this is it. And this forms, someone give me the IUPAC name. 3-pentanol oxidize to form pentan-3-one. I think it sounds a little bit nicer with 3-pentanone. But you're not wrong. Pentan-3-one is correct. What else? Correct. Nothing else. Can't do reduction, can't do acyl addition. Those were all things we saw in the alcohols chapter as well, but that was the reverse. That took carbonyls and took them away. So we're ready to move on from our previously seen reactions to new ways to form aldehydes and ketones. Good news. That's it. Now, maybe that's not totally fair because we're going to look at some reactions with aldehydes and ketones that are reversible. So we'll be able to react an aldehyde and ketone to form, say, an acetal, and then we'll be able to hydrolyze the acetal back to the aldehyde or ketone. So if anything, I would maybe just add here, nothing new except, oh, you know what? Oh, bummer. Yeah, maybe there is something I want to show because I was going to wait until section 20 and 21 with the carboxylic acids, but maybe it just makes sense to bring it up now, right? I mean, this is always the hard part. Should I wait until we have a good reason, or should I introduce it now? I think I should introduce it now. I just want to make sure that I've got the best the best examples for us. All right. Okay. Yeah, I did get your hopes up. I would say in the past I've skipped this one, but I put this one down because I wanted to show it. Reduction of carboxylic acid derivatives. I think you guys know, like, that's actually my favorite part, is to be able to put up something and say, look, you've learned so much already that I have nothing else to teach you. I think that this works so well that we're not actually going to give a different example for everything. What I'm going to show is how various carbonyls, various carboxylic acid derivatives, can all be used to form the same aldehyde with the same reagent. So what I'm going to take here is propane nitrile, or I think we could also call it cyanoethane. Yeah. Propane nitrile. I'm going to take a propanoate ester. It doesn't matter what the ester linkage is. I'm going to take propanoyl chloride. Because we can do this with the nitrile, we should also be able to do this with the amide. So the last one, and maybe I should have put this in a better order of reactivity, but the last one we'll take is a generic propanamide. It doesn't matter what the nitrogen groups are, once again. And now I'm highlighting that all of these reagents, all of these starting materials, react under the same conditions, and they'll give the same product. You guys recognize that's only because they share the same carbon chain, correct? 3 carbons, 3 carbons, 3 carbons, 3 carbons. Okay? First, we're going to react this with Dibol. Second, we're going to follow it with an aqueous workup. I want you to notice, and maybe my font is not the best, Dibol is actually DIB aluminum, AL, not AI. But I can't put a capital L because that's improper scientific notation for elements. H. Dibol is di-isopropyl aluminum hydride. What does that mean? Oh, I'm sorry, not isopropyl. Diisobutyl. The bulkier, the better here. When we say that it is an aluminum hydride, what does that mean? It acts as a source of, you're right, there is an ALH bond. It acts as a source of what? Acid. Quite the opposite of acid. Hydride. IDE implies negative charge. not OH minus, that would be like hydroxide. Hydrogen anion, H minus, which we saw with sodium borohydride, NaBH4. That was a source of H minus. Lithium aluminum hydride, that was a source of H minus. So this is aluminum, 2 isopropyl groups, and the hydride. Isobutyl. Did I say isopropyl again? What's the counter ion? Trick question. There is no counter ion. Aluminum likes 3 bonds. How many bonds does it have? Just 3. I want you to compare this to LaH and NaBH4 LaH and NaBH4 have 4 equivalences of H minus, essentially. Hydrogen is more electronegative than aluminum and boron. So hydrogen owns all of those bonding electrons. NaBH4, LaH, they can do reduction 4 equivalences apiece if everything goes well. What about dibol? 1 reduction apiece, correct? If I took LaH and I reacted it with a nitrile, I would completely reduce it. If I took LaH and I reacted it with an ester, we've learned this. It reduces it all the way to an alcohol. If I take LaH and I react it with an acid chloride or even NaBH4, all the way down to an alcohol, that's a 2 equivalence reduction. We talked about that too. 2 equivalence reduction. What if I want to do just 1 reduction and stop it before the second reduction occurs? Dibol allows me to do that. Dibol is a 1 equivalence reduction reagent. It's still a strong reagent. It has hydride in the name. But all of these reagents get reduced to propanol. Here's the 1, 2, 3 of propanol. And there's how each of those precursors have those 3 carbons. The carbonyl carbon and the nitrile carbon all get reduced down. I think we'll review this in a second when we look at reactions with aldehydes and ketones. But we can use dibol to reduce an aldehyde. We can use dibol to reduce a ketone. If dibol is strong enough to reduce amides and nitriles, which are the least inert of these carbonyls, then dibol is also strong enough to reduce an aldehyde to an alcohol. But the benefit is all of these reagents, they require 2 equivalences of reduction to get to an alcohol. Dibol is a 1 reduction reagent. So, Sam, you had a question?
Would it be important for us to know, like, the byproducts? Like, would there just be, like, a chloride ion hanging out?
Good question. No, I will not require you to know the byproducts here. Although I think that you could imagine whatever nitrogen byproducts will kick off are going to potentially bond to the aluminum, because aluminum is an electrophile. It likes to take, it's a Lewis acid, likes to take electrons. Nitrogen likes to give electrons. The OR group, whatever alkoxy group is generated, can bond. The chloride can bond. Again, the nitrogen groups can bond. And then there's also this aqueous workup. So then you can think, well, whatever is happening in this aqueous workup, maybe I'm producing ammonium because there's a lot of acid. Maybe I'm producing an alcohol or HCl. Yeah. I won't require you to know the byproducts. That I think gets a little bit too far. But do you guys think it would be beneficial for you to see the mechanism? I'm not going to test you on the mechanism here. But would you like to see the mechanism for this? No? Okay, I think what I'll do is just give you a generic. I'm not going to give it to you for all of them. Instead of R, I'm actually going to put Y. R is usually an abbreviation for a carbon group, and I don't want you guys to get that mixed up here. So Y would be the nitrogen, the ester linkage, the chlorine, or the amide linkage. In the first step, the hydride will bind to the carbonyl carbon. That's the reduction. Oops. Feel free to draw in the hydrogen because it's now there. We can also assume it. During the aqueous workup, we help this process go forward. The carbonyl will reform, and whatever that R group was gets kicked off. Or sorry, whatever that Y group was gets kicked off. Is this an addition reaction, an elimination reaction, or a substitution reaction? What would you say?
Substitution.
Yeah, I'm going to substitute whatever this group is for a hydrogen. It's a little bit more complicated when we look at the nitrile, and that's because the aqueous workup is where the oxygen actually comes from. Did you guys recognize that for all of these other reagents, the carbonyl just stays there, the Y group leaves, but with the nitrile, oxygen actually has to be added in during the aqueous workup. Okay, and now there's nothing else to learn. Like that or you hate that? You like it. It's good stuff. I think it's really cool to be able to do a one-step reduction. Okay, I want to give you some context. If we had used LAH here instead of dibol, we do have a similar process to this, where H attacks the carbonyl, and then we can potentially see the carbonyl reform, but because LAH or NABH4 both have a second equivalence of H minus, it can do a second reduction. It can take that aldehyde down. I think I misspoke there. NABH4, not strong enough to do that second reduction for most of these. Again, generic mechanism, not an exact mechanism, especially for all of these, but hopefully it gives you a perspective of what is happening. I just taught my OCHEM 1 class yesterday, all of the different classes of reactions, addition, elimination, substitution. And then I like to say subclasses of reactions like oxidation and reduction. And what we just clarified is that when we say reduction of carbonyls, we're we're actually, in this case, looking at a reductive substitution. And if we took an aldehyde and reduced it to an alcohol, that would be reductive addition. So there's every reaction can be thought of as addition or elimination or substitution. And then they can also be described with oxidation, stuff like that. All right. We're going to move from here into reactions with aldehydes and ketones. So let's think of all the ways we've previously seen reactions with these starting materials. Can you guys tell me, did we see a reduction of aldehydes or ketones in OChem 1? Or sorry, reactions with aldehydes or ketones in OChem 1? We formed them a couple of times, but that was it. Which means the first time that we saw aldehydes and ketones reacting was actually section 15, the first new section that we covered in this class. What did we learn how to do in the very first section? Before we learned how to do EAS, before we learned how to do NAS, what did we take aldehydes and ketones through? Oh man, my brain is so slow. I hate this. I forgot an oxidation. The selective oxidation with MnO2. Yeah. You guys know it. Put it in your notes. I'm going to leave a note that I am bad at my job. That would have been 4, I think. That's not where it belongs. This belongs in the oxidation.
Are you asking about
Oh yeah, reactions with. What was the very first reaction with aldehydes and ketones that we learned? MCPBA is a reaction with alkenes.
Right. Oh, with the ketones, not to. Oh, wouldn't that be one to obtain also?
Is it protonation?
Not protonation.
Protonation.
Bromination? We learned how to brominate an aldehyde or a ketone? I don't think so. So, oh man, you know what? That was another way to synthesize it that I skipped over, right? Roll back the tape. Put these back in there. Yeah, there was another way to synthesize that we missed, which was EAS, alkylation, or acylation. This is synthesis, sorry. This is synthesis of aldehydes and ketones. We can use acylation to synthesize aldehydes and ketones. Let's look at the smallest one, which would be formyl chloride. To form benzaldehyde. That's what you were thinking? Which is good. I'm glad you guys thought of it because my brain didn't. Shoot. That is a way to synthesize aldehydes, specifically benzaldehyde. We saw it most often in synthesizing ketones, specifically aryl ketones, ketones connected to an aromatic ring. So that's good. I'm glad you guys reviewed that. But there was actually a reaction with aldehydes and ketones. This is not a reaction with an aldehyde or ketone. Oh, that's a bad example because that is an aldehyde. But usually we had an acid chloride there. It is also an acid chloride. This is a terrible example because it's both an aldehyde and an acid chloride. And I would argue it's not because it's an aldehyde that this is a reaction that occurs. It's because it's an acid chloride. That's why this reaction occurs. So that's a way to synthesize an aldehyde from an acid chloride, a way to synthesize a ketone from an acid chloride. But what was the very first reaction we learned to do something with an aldehyde or a ketone? And we learned it before we learned EAS. Remember that we reduced aldehydes and ketones with the Clemmensen reduction and the Wolff-Kishner reduction down to alkane. So I'll give an example. Benzaldehyde with a para ketone. Is it important that this is para-substituted? No. Just giving you an example that Wolff-Kishner reduction occurs with aldehydes and with ketones. It's not selective in that way. We have the Clemmensen reduction. Now, I am really mindful of how I give you guys notes because I want your notes to be well organized. I want them to be thoughtful. Obviously, I make some mistakes with that. Luckily, most of you take notes on electronic devices these days. Not me. But I also want them to be well spread out. So what I don't like about this example, if you come back and look at it, you're only going to think that Wolff-Kishner reduction occurs at benzylic carbonyls, because both of these examples are benzylic. And that's just not true. So what could we do to clarify that Wolff-Kishner doesn't have to be benzylic? We could add in another carbon chain here and just push it really far away from the ring. 1, 2, 3, 4, 1, 2, 3, 4. To show that it doesn't have anything to do with being benzylic. Does that clear it up? Then for the Clemmensen reduction, I'll keep it similar. We're going to keep we'll keep a benzylic ketone. And I'm also going to have this totally non-benzylic aldehyde. Does that look okay? We use this zinc-mercury amalgam with hydrochloric acid. And how the heck am I going to fit that carbon chain on the board? one thing that I am not happy about, I think I brought this up. One thing I'm not happy about with your textbook is that your textbook really introduces these reductions early on, never explaining that they can be done at non-benzylic positions. And I will agree that this reduction is useful at benzylic positions. We saw how this reduction can help us with EAS and can help us with getting the substituted benzene product that we want. But it's also important to recognize that these reductions happen anywhere.
Do they happen with just like benzene alkanes, non-aromatic?
Thank you for asking. This is non-aromatic.
Right.
This is not benzoic.
So like if I didn't have, I mean, in the example you always use like a benzene ring. So I'm assuming like if I just had like a ketone with no ring, it should be the same, right?
Good. Good question. Let's see if we can clear it up. Let's just give another example. Yeah? I don't need that. That helps, right?
Yeah.
You know, I don't know. I want to be careful. Having an electrophile like a bromine, or I should say a good leaving group like a bromine, in the presence of nucleophiles like hydrazine and potassium hydroxide, I think I want to be careful. So I'm just going to show how there's an alkene. So what I'm trying to highlight here is there can be other functional groups in the molecule, and the alkene, sorry, the ketone or the aldehyde, those are the ones affected. Now, to clarify, Caesar, sorry. This ketone, being so far away from the aromatic ring, it's not getting any electronic support from the aromatic ring. It's also probably not getting any steric strain from the aromatic ring. So looking at this, you could pretty well say it has nothing to do with the aromatic ring. Same thing with this, really has nothing to do with the aromatic ring. But you're right, I did want to have an example where you could see that benzylic is reduced and non-benzylic is also reduced. But this helps clarify that too, right? Has nothing to do with the ring. Good. Maybe a cooler example I could have given too. I like cyclohexanone. So we could do the Clemenson reduction of cyclohexanone to cyclohexane. All right. I think maybe you could argue that we saw aldehydes and ketones during the EAS and NAS reactions because they are deactivators in EAS, they are activators in NAS. They're meta-directors in EAS, they're orthopara-directors in NAS. But is it really because of the aldehyde or the ketone? Not really. So I think reactions with aldehydes and ketones, maybe they don't need to involve EAS and NAS. Do you guys think that would be worthwhile putting in this review section? They have effects, but they are just part of a family thing. Then we need to move into our alcohol section again, where, once again, we saw this quite a bit. So let's look at reduction to alcohols. And I think once again here, I'm going to put several examples so that we can see how different substitutions react differently. So let's start with formaldehyde, CH2O. This can be reduced with NaBH4 or LAH or a new reagent. One that's still on the board. No, you're looking at it, Sam.
Is it aluminum?
Well, this is aluminum. Diol. There you go. Yep, hydride. Diisobutyl aluminum hydride. So I'm just going to highlight that this is new. But I want you guys to think about this. Where is hydride, H minus, stronger? When it's bonded to a boron or when it's bonded to an aluminum? When is the hydride stronger? When can it take its electrons more willingly and use it to attack even less partial positive carbons?
Boron.
So you guys have different answers. I'd like to hear your thoughts.
You said the aluminum was more electronegative.
I did not say that.
You said it wants the electrons, and nitrogen donates the electrons.
I did say that it is an electrophile. It's a Lewis acid, which is almost the opposite of being electronegative.
Reverse my answer.
So we can think of this a couple of ways, but I want to hear from you guys. Where is hydride stronger when it's bonded to boron or aluminum?
Don't the LAHs, that was like the only one that could produce carboxylic acid and esters, so it's, I guess, would be aluminum.
Good.
Stronger.
That's using evidence, or I guess just like the evidence of what I've said. That's using your evidence to say hydride is stronger when it's bonded to aluminum. It's more aggressive when it's bonded to aluminum. It can take its electrons and really go to anything it wants to when it's bonded to aluminum. Now I want you to explain, why is it stronger when it's bonded to aluminum?
I mean, aluminum's not electronegative, and so if it's, it would rather have a positive charge over a negative charge, so it's really partial positive, and that's really negative because it doesn't want those electrons.
I think we could make the same argument about boron.
Boron's a little more electronegative.
Okay, there we go. That's actually it. Boron and aluminum are in the same family. Boron is higher up. Electronegativity increases up a row, or up a column. So boron is more electronegative, which means that boron holds onto the electrons with hydrogen a little bit better. Aluminum, larger, less electronegative, lets go of the electrons. And you're not wrong that aluminum is happy taking on a positive charge, maybe even more willingly than aluminum. Sorry.
Boron.
Aluminum takes on a positive, maybe more willingly than boron. Takes on a negative, maybe less willingly than boron. So why is LAH stronger than NaBH4? It's because aluminum is less electronegative, hydrogen has more range. So, if hydride attached to aluminum can reduce a carbonyl, then why shouldn't hydride attached to aluminum be able to reduce a carbonyl? The distinction here is the equivalences of reduction. LAH can do 4 equivalences per molecule. Diol can only do 1. So we have this example. This is what I'm trying to I just don't want this to be confusing. Dibol is a great way to synthesize aldehydes from more oxidized carbonyls. If you were to add dibol in excess, if you were to add dibol in 2 equivalences, yeah, you do run the risk of reducing your aldehyde. Its only benefit is that dibol has only 1 equivalence. I also just thought about this. I never made this clear. You saw that list I had earlier? I didn't put anhydrides, not because anhydrides won't work, but I don't think anybody does that with anhydrides. Maybe I'm wrong. But there was another carbonyl I didn't put on there, which was carboxylic acids. Carboxylic acids, we're not going to see those being reduced here. So I want you guys just to think about those reactions, and I want you to realize dibol is just as strong as LAH. That's why dibol can react with esters. That's why dibol can react with amides and nitriles. It's just as strong, it's just fewer equivalences. Okay, this is not maybe the best way to have this all formatted, but that's step 1, and this should be followed by an aqueous workup. So whatever reducing agent you want, try to follow it up with an aqueous workup. If we take an aldehyde, just a normal aldehyde, oops, tricked myself there, put PCC. Once again, we can use any of our reducing agents followed by an aqueous workup, and we can reduce these to a primary alcohol. And with our ketones, we can reduce our ketones down to a secondary alcohol. I want to point out a small change that I just did. In these last 2 examples, I put LA-H, LA-H. Doesn't really mean anything, if only to emphasize the fact that it's a source of hydride. So it just kind of exaggerates the fact, or emphasizes the fact that you've got an LAH bond.
It should both be aromatic rings, right?
Oh, you know what? I wanted it to be cyclohexane.
Okay, so neither of aromatic rings.
Yeah,
Okay.
and then I think because I got so used to drawing 6-membered rings with benzene. You know, I started putting that circle in my OCHEM 1 class, and I really, really try to avoid using a circle in an aromatic ring until I explain it in OCHEM 2, because I even told you guys, it's bad. The circle in the ring is not accurate. All right. Similar to these lines, we saw acyl addition to alcohols. So we can look the same. We can start with formaldehyde. And we can take any sort of organometallic followed by an aqueous workup. We can get a primary alcohol. If we take an aldehyde, and I'm going to revisit the fact that we can really swap where the carbonyl and where the organometallics show up. Sam, give me a number between 1 and 6.
4.
4. Isobutanol. I want to highlight the fact that we can swap where the aldehyde and where the organometallics show up. It really doesn't matter, just so long as these two reagents are followed by an aqueous workup.
So these are just examples. Or
Yep.
sizes.
This everything is just examples, right? Everything today are just examples of different reactions. What I'm highlighting with the 1, 2, and 3 are the 3 major types of aldehydes and ketones, which is formaldehyde, aldehyde, and ketones. Okay, with number 3, though, I thought I'd show you it a bit different. Rather than having a 1, 2 over a reaction arrow, I thought I'd show you carbonyl and organometallic, and then over the reaction arrow, clarify that there will be an aqueous workup. That's what that says. Aqueous workup, AQ workup. But you can just put AQ, wiggle, wiggle, wiggle. You guys ever seen those TikToks or memes that are like notes my organic chemistry professor left on my exam? No, maybe those only come up for me. Some professors have some really bad handwriting, and it's like, even from my perspective, I look at the question, I have no idea what the comment is that they've left. Have you guys predicted the products here?
I
One-
started to on this one, but I'm confused because that couldn't go there.
Could it?
Alcohol. No, because the double bonds and that couldn't be bonded to 3.
Count your carbons. Map your carbons. Remember how I like to count through a nucleophilic attack so that I can lay out everything? And keep in mind you don't need to number every carbon. Just enough of them that you can keep track of what's going to form. Yeah, there you go. There you go. Good work. No, sir.
Nope.
Acyl addition. Where's your alcohol, right? exactly it.
Would it be this or would it be?
So this carbon is going to attack where?
I mean, I thought this to the.
Sure, maybe lithium to the oxygen, but lithium doesn't own these electrons. Carbon does. So your carbon is going to attack the partial negative oxygen over the partial positive carbon. Nucleophile to electrophile. Carbon attacks carbon. One of the benefits of our, yep, you got it. One of the benefits of organometallics, creation of carbon-carbon bonds.
I don't know why I like these.
You don't like these?
Is there a difference?
And you don't know why?
No.
Okay, rude.
Yeah.
The reason you like them is because chemistry is fun.
Well, it's kind of easy to understand as far as you know that the organometallics can attack the carbon, and then that's it. It is as simple as that.
Yeah. Except for cuprates, where if you've got a cuprate won't attack the the carbonyl carbon, and if you've got a conjugated carbonyl, the cuprate will attack at the conjugate position. We're going to see that in Unit 5.
Okay. Never mind. I don't like them.
No, I think you just don't like cuprates, and that's okay.
Yeah, I don't think I use them at all. For that.
No, we didn't. You're right. We didn't because they're not that useful. Yeah, you got it. Good. Good review, right? Okay. That's it. Those were the reactions we saw with aldehydes and ketones coming into this. So now we're moving into new reactions. Man, I'm just going to kick myself if there are more. Just trying to run through it in my head. Yeah. So the first one that I want to cover with you guys is hydrolysis. And I do want to talk about what that word means, hydrolysis, because it is a word that will be very prevalent in this unit. Hydrolysis means what?
Water. Like, there's water involved.
There's water involved. Water means reaction, or hydrolysis means reaction with water. Yep. Hydrolysis is a noun. The verb form of hydrolysis is to hydrolyze. So if we want to hydrolyze an aldehyde or a ketone, that means that we will react it with water. We're going to do this in two types of conditions: acid catalyzed conditions and base catalyzed conditions. So if I take formaldehyde and I put it in a solution of water and acid, I'll make methane diol. I do want to emphasize the fact that this is an equilibrium reaction. So to do that, I'm going to put over the reaction arrow a reverse reaction arrow. The aldehyde is catalyzed to form a gemdiol, and the gemdiol is catalyzed to form an aldehyde. I made a mistake here. I apologize. Don't copy down what I had. CH2OH. I'm trying to put formaldehyde. That should be CH2O. And then you can see it becomes CH2OH. What has changed? CH2, CH2. Nothing changed. O to O, H2O. There's been an addition of water. If you're interested in showing this molecule in a condensed format, this would be maybe the best way to show it. You could also put something like CH2OH2. It's not really an easy, pretty way to draw it.
Do we have to put the double?
No, if you don't want to, you don't have to. But I do want you to recognize that it goes forward and backwards. Because we're actually going to take advantage of that at some point, the fact that this can be reversible. So we go from 2-methylpropanol, to 2-methyl-1,1-propanediol. And the equilibrium lies heavily towards the ketone. That's not the word I wanted. The equilibrium lies heavily towards the carbonyl. That equilibrium does not lie towards the diol. After I drew that first aromatic ring, I realized I didn't want to draw any aromatic rings, so excuse me for having both an aromatic ring and a pH. Now I do want you guys to think about the conditions here. These equilibria lie more heavily towards the carbonyl in most instances, but they're not equal to each other. So I want you to suppose which of these three instances the equilibrium lies closest or lies more towards the diol.
Last one.
Yeah, the ketone. I think the ketone lies closest to the diol, and then I would assume you mean formaldehyde lies closest to the carbonyl. What about the fact that water has to be a nucleophile here? And so in every case where water has to be a nucleophile, where can water attack the easiest?
There's nothing around.
So where would that be?
First one.
Right. So water as a nucleophile has an easier time doing acyl addition to formaldehyde, which means equilibrium lies furthest to the right for the formaldehyde. If you have an aqueous solution of formaldehyde, it does form quite a bit of its gemdiol. But if you have an aqueous solution of a ketone, let's say acetone, its equilibrium is maybe 5 parts gemdiol to 95 parts ketone. It's not a lot. So if this is something you want to try and take advantage of, it's difficult to, because equilibrium doesn't support it. All right? The other way that we can get here is by base catalyzed conditions. What I'm going to do to sum this up a little bit nicer is just give us some examples and show how they all utilize the same conditions. They all utilize the same reagents. H2O2 with NaOH. And once again, I can form methane diol. In this other molecule, I've got 1,1 ethane diol, and then here I've got 2,2 propane diol.
And here there's no double equilibrium.
Yeah, there is equilibrium here as well. I wanted to just summarize this a little bit faster, and it is harder to show my equilibrium arrow because I've got kind of this grid format. So if you wanted to, you could put something underneath here that says equilibrium. Now, suppose you don't have water, but instead you have an alcohol. Do you remember that water is a precursor reagent to forming an alcohol? Water, alcohol. Alcohols are a precursor to what group? Ethers. So what we'll do when we pick up tomorrow is we'll look at our next reaction.
Tuesday.
No, you guys are coming in Friday. We're going to look at the hemiacetal and acetal formation. We're not going to see a base catalyzed acetal or hemiacetal formation. So just to clarify, hydrolysis to the gem diol, that occurs with acid catalyzed conditions and base catalyzed conditions. The acetal and hemiacetal formations, we're only reviewing those in acid catalyzed conditions. Deal? After we review some of those reactions, we're going to look at the mechanisms for all of these. The mechanisms are very straightforward. They make a lot of sense. And the mechanisms for acetal and hemiacetal formation very likely will be on your unit test and your final exam. So these are mechanisms that we're coming back to again and again for the rest of the semester. All right?
The question, the homework is due tonight.
You're right. I forgot to change the due date for the homework tonight. I'm going to move that due date to probably next week, Wednesday night. I do want you guys to still have time to submit it and get it in before the unit test, which is next weekend. So, I mean, you can give it a shot, and I'll try to grade it Friday. But I'll move the due date so that you guys have much more time to look at it. Yeah, thank you. All right, guys. Have a great day and a good weekend. See you next week.